Here are some questions I'd like to answer in this video. Number 1, what is the linear charge density of, say, copper? 2, what effect does Lorentz contraction have? And 3, do the minuscule changes in length create a measurable effect of force? So I'll start with the first question. What is the linear charge density of, say, copper? As it happens, copper contains about weighs about 63.5 grams per mole. It has a density of 8.96 grams per cubic centimeter. And there is generally about one charge carrier in copper per atom, so you can calculate the number of charge carriers in a cubic meter of copper as 8.48 times 10 to the 28th charge carriers per cubic meter. So that really is quite an enormous number. Even a small difference between the observed densities of the material might create a significant electric field. But what I'm wanting here is the linear charge carrier density. This is the volume charge carrier density. I'd probably say that this N 8.4 times 10 to the 28th per meter cubed is equal to the number, you know what, I think now I would rather call this number rho of copper rather than the number. We'll call that the density, the volume charge carrier density. And then I can say that rho is equal to N over the length of the thing times the area of the thing. And so that's the density, and then we can find the linear density, which previously they called lambda on the Wikipedia site. They called it lambda. So this is just N over L, which would be rho times the area. If I multiplied both sides of this by area, I would get equal N over L. So now the electric field from that phenomenon we already got earlier. Well, we didn't derive it, we just pulled it from Wikipedia. So this is rho times the area of this cross-sectional area of the conductor divided by 2 pi r epsilon naught. And epsilon naught is called the permittivity of free space, or the electric constant. It's a truly tiny number. So for copper, the knowns are, we will know rho, we will know 2 pi epsilon naught, and the only things left over are the area and the radius. So using the density of copper and the permittivity of free space, we can find out that this will come out to about, wait, I wanted a 2 pi in there as well, so let's put that 2 pi in. That comes out to be about 1.52. Let's call it, so it's 1.5 times 10 to the 39th times the area, the cross-sectional area of the conductor divided by the distance from the center of it. And that is the linear carrier density. No, it is not. That is the hypothetical electric field due to the linear carrier density, which would be in, what, newtons per coulomb. And that is just if somehow you manage to remove all of the atoms except for the free electrons in there, this would be what the electric field would be. 10 to the 39th newtons per coulomb, which is really enormous. 10 to the 39th volts per meter. those two units are interchangeable, the newtons per coulomb and volts per meter. Okay, the next thing I want to talk about is the fractional change that comes as a result of Lorentz contraction. And it goes L equals L sub naught divided by the square root of 1 minus V over C, quantity squared. So I'm just going to talk about this fractional change, L over L sub naught, which will just be 1 over square root of 1 minus V over C squared. And I think the way to set this up would be, well, to consider three different velocities. We've got the atoms are going to be moving at one velocity, the electrons are going to be moving at another velocity, and maybe the third velocity is going to be the observer velocity. So we'll say the observer is moving at speed 0. The positive charges are moving at speed v, and say the electrons are moving at speed v minus v sub naught, or v plus v sub naught. I don't care what. And what we're concerned about here is the relative densities as the observer sees the density of the positive charges, the linear density of the positive charges, and the linear density of the negative charges. So I'm thinking of it as the linear density of the positive unpaired charges, because the positive charges are surrounded by a lot of electrons that are not in the valence shell, that are not conductive, that are not moving. So we're just concerned about the ones that are associated with the ones that are moving. And then we've got the linear density of the negative carrier charges, which are moving. And then these are going to be moving at velocity v with respect to the observer. These are going to be moving with v minus v, let's call it VE, whatever the electron velocity is, and maybe that would be better referenced as a positive number or a negative number. It depends on your peculiar example, because in this one I wanted to consider the observer moving this way, then the velocity here was that way, and the velocity here was that way, so I was thinking of this as a negative sign, but just make sure your sign conventions kind of work out. Now this number is going to be really, really close to 1, so for both v and v minus ve. So I'm going to rewrite this kind of like the original density, rho over a times will be 1 over square root of 1 minus v over c squared minus 1 divided by square root of 1 minus v sub e over c squared. Though I don't guarantee that all of the signs are correct. What's going to happen with this is, since this velocity is actually going to come out way less than 1 meter per second, the drift velocity of, or no, v sub e is going to come out way less than 1 meter per second. It's the drift velocity of the electrons themselves. We'll look at a couple of different options for how to approach this. One, you might call this cosh of phi, where phi equals hyperbolic tangent of v over c, and call this one cosh phi 2, where phi 2 is the hyperbolic tangent of v minus v sub e over c, and then try subtracting those and see what comes out. What I'm going to do is use something called a power series expansion. This is also called the Maclaurin series expansion or Taylor series expansion. So the series expansion is basically turns this function into a polynomial, and this generates the polynomial expansion that you would have, around x equals 0. So when I plug 0 into here, I just get 1. And also it has 10 terms, or up to 10 terms, because it has the x squared term all the way up to the x to the 10th term. Now I went ahead and plugged in this entire expression and found the first and second term of the series. This looks as though it may be more complicated than I was hoping. So that looks quite ugly, but what if I put in specific values for the speed of light and the electron, or for the carrier velocity? This actual carrier velocity was calculated by assigning a copper wire with a 0.0 what is that, a 1 millimeter radius, and finding the area of the wire, and using an equation for the velocity of the carrier given on Wikipedia. I used 1 amp. This is the number of particles per, this is the actual density of a copper wire, charge carrier density. A is the area, and Q is the charge on the electron. Anyway, when I plugged it into that formula, I got this of 0.00002 meters per second. And when I plug that in to the equation, I come up with a value of, looks like negative 2.6 times 10 to the negative 22nd times the velocity. That is the ratio of, I think that it's not a ratio, it's a subtraction, gamma 1 minus gamma 2, basically, given those particular velocities. We still need to multiply that by rho over A, which was 1.5 times 10 to the 39th, which gives us the apparent charge density. And then let's divide that by the charge of, because that would be in fundamental charge units, so let's divide that by 1.6 times 10 to the negative 9. And that gives us the number of apparent coulombs per unit, coulombs per meter. So now I think at least we have one example. We have a copper carrying 1 amp of current and something passing by with velocity v. And also we have a charged wire carrying a charge of 0.063 coulombs per meter, 0.063 v, so I actually will multiply this number times the velocity to find how many coulombs per meter. We can adjust it by adjusting our velocity. And so we come back to the question, is f of b the same as f of e? And we can shorten that by dividing out this 2 pi r, and our question is 0.063 coulombs per meter divided by epsilon naught equal to mu sub naught times our current 1 amp. Okay, I made a mistake. I am comparing E field to B field. Those shouldn't be the same. What I want to compare is QE, so I'm going to multiply this thing by, still going to go ahead and divide by 2 pi r, so force over 2 pi r, QE over 2 pi r, and force here, divide by 2 pi r, divide by 2 pi r, and so I'm going to be comparing that to equal to, would be QV mu sub naught I, but this lambda is 0.063 V, 0.063 V, so essentially I'm afraid I cancel out the V, we can cancel out the Q, and I'm left with what I started with, 0.063. 0.063 equals mu sub epsilon naught equals mu sub naught times 1 amp. I think that's what I had before. Shouldn't be erased. Well, the good news is that I did get a quantity that is simply directly, basically a linear charge density that is directly proportional to velocity here. So the force is directly proportional to, so the force is also should also be directly proportional to the velocity. And I have a force that is directly proportional to the velocity here, because the B field is proportional to the current, or no, it's proportional to the, directly proportional here. The force is directly proportional to the velocity. The bad news is somewhere along the way, it looks like a bad value got creeped in, because mu sub naught epsilon naught is, I believe it's 1 over c squared, which is definitely not equal to 0.063. Yes, in various SI units, epsilon naught is 8.85 times 10 to the negative 12th, and mu naught is 4 pi times 10 to the negative 7th. And when you take 1 divided by the square root of mu sub naught times epsilon, you get 2.99 times 10 to the 8th, which is the speed of light. This comes out in meters per second if you put in all these. So we're off, well, this would be, this equation here says 0.063 equals 9 times 10 to the 16th. So we're off by 16, off by about 18 orders of magnitude, which really reminds me of the number 1.6 times 10 to the reminds me of the charge on an electron, 1.6 times 10 to the negative 19. And I will tell you, I threw in that 1.6 times 10 to the negative 19th kind of as an afterthought, because I thought that this number seemed too large. What was it, too large? So I'm not entirely sure if that was entirely reasonable. Let's cross it out and see. We get this huge number here, 3.96 times 10 to the 17th. And that 3.96 times 10 to the 17th is still off by a pretty wide margin. It actually turns out it is a factor of 4.4. So, off by a factor of 4.4 times. But really, I'm probably going to have to restart this problem from scratch later on to see if I can find what I've done right and what I've done wrong. But what I'm hoping is, in the end, this turns out to be a way of deriving the mu sub naught epsilon naught and the ratio in between them, and kind of showing a perfect equivalence between the Lorentz contraction effect and the magnetic field.